Gradient descent is a first-order iterative optimization algorithm for finding the minimum of a function. It tweaks its parameters or coefficient iteratively to minimize a given cost function. The model stops learning when the gradient or slope is 0. Gradient descent algorithm has two steps involved. The first step is to initialize the parameter by some value. The second step is to calculate the derivative of the cost function for each iteration and to simultaneously update the parameters. The equation for gradient descent is, where A is the learning rate that controls the size of adjustment. It must not be too small, else the learning will take very long, and must not be too large, else the network will not get good coverage. And theta is the matrix value. Evaluate the coefficient. Coefficient describes the mathematical relationship between each independent variable and the dependent variable. Let's understand how you can evaluate the coefficient. In regression analysis, p-value is called predictor value. P-values for the coefficients show whether these relationships are statistically significant or not. When the p-value is less than 0.5, it will reject the null hypothesis. That means variables have some effect and need to be retained. When the p-value is greater than 0.5, it will accept the null hypothesis, meaning variables have no effect and can be removed. A predictor that has a low p-value is likely to be more useful to your model because changes in the predictor value are related to changes in the response variable. Demo linear regression. Problem statement. The advertising dataset captures the sales revenue generated with respect to advertisement costs across multiple channels, like radio, TV, and newspapers. In this demo, we will use linear regression to understand how spending on advertisements impacts sales. Here are some of the questions which can reveal information from the data. 1. Is there a relationship between ads and sales? 2. If so, how strong is that relationship? 3. What types of ads contribute to sales? 4. What is the effect each ad type has on sales? 5. Given ad spending, can sales be predicted? These general questions might lead to more specific questions. Let us explore these below. Let's import the required libraries and load the dataset in Pandas data frame. Import Pandas as PD. Importing Pandas data frame. Import matplotlib.pylplotsPLT. Importing matplotlib. From sklearn.metrics, import r2 underscore mean underscore squared underscore error. From math, import sqrt. Importing sklearn, libraries, and square root function. Now let's import the dataset in Pandas data frame. Let's see the data frame. Since there is no column name, let us add the headers to the data frame. The independent variables in the data set are TV. What is the amount in thousands of dollars spent on TV for a single product in a given market? Radio. What is the amount in thousands of dollars spent on radio? And newspaper. What is the amount in thousands of dollars spent on newspaper? The target variable is sales, which tells us the sales of a single product in a given market in thousands of widgets. Data.shape. The data set has 200 rows and 4 columns. Let's visualize the relationship between the features and the target variable sales using scatter plots. Initialize the scatter plot using the code on screen. Plotting TV sales, plotting radio sales, plotting newspaper sales. Looking at the output, we do see a relationship between ads and sales. applying linear regression analysis to estimate the relationship between sales and television ad spending. Let's use TV as the feature column. Here, X is the independent variable, and Y is the dependent variable. Importing linear regression model from sklearn. Initializing the model. Fitting the model on X and Y. Let us now print the intercept and the coefficient of the resulting linear equation. By interpreting the model coefficients, we can say that A unit increase in television ad spending is associated with a 0.047537 unit increase in sales. Now that we have the linear equation, we can use this for prediction. Let's say that there was a new market where TV advertising spends were $50,000. What would we predict for the sales in that market? Use the previous results to calculate the new value for sales. Let's predict the new X values. Using the above equation, we would now predict the sales of 9,409 widgets in that market. Let's make predictions for the smallest and largest observed values of X and then use the predicted values to plot the least squares line. Initializing the scatter plot for TV and sales. Plotting the least squares line. Looking at the plot, we can say that we have a high bias and a low variance model. Hypothesis testing and p-values. Using the null hypothesis, let's assume there is no relationship between TV ads and sales. Now let's test this hypothesis. We shall reject the null hypothesis if the 95% confidence interval does not include 0. Importing stat models. Import statsmodels.formula.api as SMF. Applying OLS on TV sales. Printing the p-values. im.p-values. The output shows the p-values for the model coefficients. The p-value represents the possibility that the coefficient is actually 0. In this case, the p-value for TV is far less than 0.05, and hence, we infer that there is a relationship between TV ads and sales. How well does the model fit the data? The most common way to evaluate the overall fit of a linear model is by using the R-squared value. Let's print the R-squared value. im.R-squared. Now, looking at the output, can you tell if it's a good R-squared value? Well, it's hard to say. The threshold for a good R-squared value depends widely on the domain. Therefore, it's most useful as a tool for comparing different models. Multiple linear regression. Earlier, we used TV as the feature column. Now let's take all the independent variables to build a multiple linear regression model. Most of the code remains the same. Let's use the 3 variables to build the model. Importing sklearn. From sklearn, import model_selection. Creating a trained test. Apply